How's it going, YouTube? We're going to be going over 18.3 of our aromatic reaction chapters, and this is going to involve nitration of an aromatic. So nitration is when we add an NO2 group to an aromatic compound. As you can see, we have an example with benzene here. We use nitric acid and some sort of acid, like H2SO4 is a good example, and we're going to add that NO2 group. We're also going to get water as a byproduct. Now let's get into the mechanism. Alrighty, we are ready for the mechanism here. It starts with an equivalent of nitric acid and an acid as a reagent. So what's going to happen here is to a very small appreciable amount. Let me change the color of my brush here, sorry, one moment. Okay, this oxygen, and it seems like why would you do it here because of the negative charge here, or maybe the free electrons here. Why will it specifically do this? Well, you must know that it's not just this reaction that's occurring, it's many reactions. That negative charge is probably getting neutralized by some of the acid. So it's important to know that, but for this mechanism, we're going to look at the very small equilibrium that exists with protonating this oxygen. All right, so we protonate our nitric acid. We have 3 charges on this molecule. We know that that's no bueno. We don't really like that. So we're going to have to neutralize some of these charges. And how can we do that? Well, it's quite simple. Arrow pushing. Oxygen here has a negative charge, so we can make a pi bond, right? And we could make nitrogen a neutral species. And I forgot there's a positive charge on the water. But when we look at nitrogen becoming neutral, then we look at oxygen here, and where oxygen's like, I don't really like being positive. I think nitrogen, you should be positive because you're less electronegative. And indeed, that's what happens. So nitrogen gives oxygen those electrons. It's like, be neutral. I'm okay being a little positive. So we're going to get this species here, and this equilibrium will be heavily shifted because we're neutralizing stuff, and we're going to get nitronium, a nitronium ion, nitronium, and we'll draw a little smiley face for good measure, nitronium. All right, this is our electrophile. That first 2 steps was to make our electrophile, kind of like how we saw in the sulfonation and the halogenation subsections. So we're going to take this nitronium ion, and then we're going to use it as the electrophile in an aromatic compound. So hopefully you can kind of see the pattern here. Maybe if you even want to go ahead and try and guess the mechanism, you can go right on ahead. So this aromatic compound is going to, and we'll just draw the NO again. So now this is the second part, the main reaction that's happening. It's going to come and attack the nitrogen. Let me draw that a little better. Maybe in a different color too. We need some color on these pages. It's going to pick up the NO2 group, and some of these electrons are going to be pushed into an oxygen, giving it a negative charge. And we get this molecule. Alrighty, and then we're going to have a positive charge on the carbon here, as well as we're going to also show that we have a hydrogen here, which is going to be very important in just a second. So here's where we're at. So we have our aromatic compound, we have our nitronium ion electrophile. Those pi electrons reach out to the nitronium, that specifically the nitrogen atom with the positive charge, and binds to it, pushing electrons onto oxygen, making it negatively charged. All right, we know that this is resonance stabilized, so these charges are kind of neutralized in a way. They're not very significant. So the next step here is quite simple. Restoring aromaticity, we can use the water that we lost here in this step, right? And usually that should be our solvent, right? Or part of our solvent. We could use, make this kind of acid catalyzed. It's all up to how we want to do it. But in this case, we'll just use water. I'm going to reach out to this hydrogen here, and I'll change the color to show that we're restoring aromaticity as the major important thing here. All right, and we have aromaticity and an NO2 group. Alrighty, that is the entire mechanism. Let's go through it one more time, kind of just summarize everything. So we have nitric acid, right? That's going to be our starting reagent. The oxygen here on the alcohol group is going to reach out to an equivalent of H2SO4 acid. It's going to steal a proton, become protonated to make a water-leaving group. Oxygen's negative charge on any of these oxygens here, remember this is resonance stabilized, it's going to arrow push out the water. We're going to get water as a leaving group, of course, leaving us with a wonderful nitronium ion. That puts a positive charge on the nitrogen, strong positive charge, meaning very good electrophile because of induction, right? Poor electron density on that poor nitrogen there. We then take this nitrogen electrophile on an equivalent of an aromatic compound, like benzene is what we used in this example, reaches out to the nitrogens like, hey, you want to bind to me? It's like, okay, I guess I will, right? And then to restore aromaticity from the sigma complex that we had here, we used an equivalent of water that we lost earlier to restore aromaticity, and we get NO2. All right, I have one more thing to show you, something we can do to NO2 that will become important in chapter 22, looking at amines. While I won't show you the mechanism for nitro reduction, I do want to go over it here. Basically, we turn the nitro group, the NO2 group, into an amine, a primary amine at that, NH2, bound to that aromatic compound directly. This is important when we get, of course, to the amines chapter, where we can see how we can do reactions of amines and manipulate that amine into something a little better. So there's two methods to reduce it, right? Make the oxidation number for nitrogen a little more neutral. So we can do this by using iron, tin, or zinc with a proton source from HCl, for example, just an acid there. And what that does is it goes through quite a complex mechanism that I won't share here, but you're free to look online. Quite a complex, I think it's like 15 steps at least. The metal plays a big role in binding and making sure that this reaction can occur to an appreciable amount. The second one is using palladium, platinum, or nickel in the presence of H2 gas. It's kind of like what we saw with, what's it called, hydrogenation of alkenes, alkynes, doing that, right? Kind of the similar thing there. Again, decently complex mechanism. You're free to look online, but I just thought I'd throw this in here because it's an important thing that you can do in the lab to make amines from nitro groups. So thank you guys for watching. That was nitration of aromatic compound. I hope you guys enjoyed that. If you did, drop a like. Comment if you have any questions. I will be checking the comment section throughout the series, making sure I can answer some questions for you. Thank you guys for watching. Have a wonderful day.